This is the moment we've all been waiting for. We are going to complete, more or less, the trace-determinant plane. We talked about how if we're up here, we have complex eigenvalues, and if we're down here, we have real eigenvalues, and if we're on here, we have repeated real ones. But how can we break this down even more? So let's remember that in terms of the trace and the determinant, what was our eigenvalue? We found it by looking at the characteristic polynomial and noticing that, oh yeah, the trace and the determinant appear in the characteristic polynomial. We can use the quadratic formula on that to get that lambda is equal to t plus or minus the square root of t squared minus 4d all over 2. We're going to be using this for the entire video because let's make a giant trace determinant plane. I'm going to do it on its own page. So it should be pretty big. It doesn't need to be ginormously huge, but it should be fairly big. And let's make sure to label it. This is our trace axis. This is our determinant axis. And of course, we know that we're going to have this parabola. Oh gosh, let's make it look a little nicer than that. This is our parabola that has the determinant being 1/4 of the trace. This is our repeated root parabola. We've already drawn this. But this is going to be kind of our final product for this section. We're going to build it because we already know we have complex stuff down here, up here. We already know we have real stuff down here, but let's really see exactly what's going on. So let's start with a complex solution. Complex is a little easier to start with, which I think I used green for in the last one. Maybe we can use green again. And I kind of implied, I didn't imply, I said that the real part of something that's complex is t over 2. So specifically, if we have a complex eigenvalue, well, if t over 2 is positive, that's the real part. So if the real part's positive, it's a spiral source. If the real part is negative, it's a spiral sink. And if the real part is equal to 0, we have a center. So what we're going to do is put this on our plot. And of course, t over 2 being all of these things, multiply everything by 2, the right-hand side's still 0. So we can subdivide this green area into 3 cases. If t is positive, and we're in this portion, we have a spiral source. So let's draw that. All right, if t is positive, and we're up here, we have a spiral source. So I'm going to draw a little picture in a box. Say, what does a spiral source look like? Spiral source. So we're spiraling out from 0, 0. If t is negative, we're in this portion, right? We still have to be above this line because that's what we need to have complex roots. So if we're in this portion, we have a spiral sink. T is negative. What is a spiral sink going to look like? Let's use the right colors. We're spiraling in to 0, 0. And again, we don't know whether it's clockwise or counterclockwise. It could be either. What happens if the trace is 0? If the trace is 0, we have a center. So if we're on the d-axis, then we have a center. That's going to look like some kind of ellipse. Again, who knows what kind of ellipse? One of these ellipses. So remember how at the start of this section I said we have all of these information about our eigenvalues and eigenvectors and our qualitative behavior? Could we graph that in a way so that we can see how it interacts and where they like kind of cross into each other? That's what we're doing with this trace determinant plane. We notice that if we're above this parabola, if we're in the first quadrant and above the parabola, we have a spiral source. If we're in the second quadrant and above here, we have a spiral sink. And what happens when the source becomes a sink? In that special moment, right between a source and a sink, it doesn't spiral at all. The spirals meet and we get ellipses or circles. And that's a center. And then we're going to talk later about that. This is essentially what a bifurcation looks like. With a phase line, a bifurcation happened when we went from like, a lot of times it would be from a sink to a source and we'd have a node. Well, this is very similar what we have here. But there's going to be other transitions too. Because remember, if we're above this, we have complex. If we're below this, we have real. So we're going to also be able to see what happens as we're crossing this. So let's do that next. And this is where things get a little bit more complicated. So complex analysis was not too hard. Let's copy this down to a new page and do what happens for real things. And again, let's copy down that our lambda will be t plus or minus the square root of t squared minus 4d all over 2. That'll be important. So I want to preface this by saying I really would like you to do this analysis, but it's not something I need from you. So if you're getting a little overwhelmed, feel free to just pause and kind of enjoy the math, enjoy the wonder. I don't want learning to get in the way of I don't want the pressure of learning to get in the way of actual learning and love for math. So feel free to kind of just take the conclusions and watch the process if trying to follow along the process is overwhelming. Otherwise, pause the video, try to work things out on your own, and we have some cool things. So there's a lot of situations for if we have real eigenvalues, and it's a little hard to see. Complex was kind of easy, but real is much, much harder, because real, it mattered whether the eigenvalues were the same signs or not. So same signs could be both positive, could be both negative, it could be one of each. And it's a little confusing because we have this plus or minus. So the relative size of each of these quantities really matters. If t is bigger than this square root and positive, they'll be the same size. Or again, if it's bigger in magnitude and negative, they'll also be the same sign. But if t is relatively small compared to this square root, then they'll be opposite signs. So we're going to break that down with something called cases. So we're going to break this into cases. Because it's overwhelming to try to think of everything, every possibility that could happen. So we're just going to write down what happens if this is the case. What happens if this is the case? We'll have some subcases as well. So let's start and say, okay, let's just not worry too much about some things. Let's suppose that the trace is positive. If the trace is positive, what do we know? Well, we already know immediately what one of our eigenvalues is. If the trace is positive, then one of our eigenvalues is found by the addition portion. Positive plus positive is going to be positive. So we know one of our eigenvalues is positive. If the trace is positive, we can never have a sink, for example, because sinks require both eigenvalues to be negative. So we might be curious, when is the second eigenvalue also positive? That would give us a source. Well, the second eigenvalue is also positive if this is small enough. How small is small enough? Well, we're really curious, right? I'm going to write this off to the side. We're really curious because we know we have a source when t squared minus 4d has a square root that is smaller than t. And when is that going to be the case? Well, that's not quite easy to find out. But a few ways of approaching it. You might just jump immediately to the direction, but you might be able to. I'm talking a lot. Of course, it depends on d. And if d is positive and if d is negative, different things happen. So we're going to look at a subcase. Suppose that D is positive. Well, if D is positive, I guarantee this is true. Because if D is positive, well, if I have two things that are equal and I subtracted a positive from one, it got smaller. So if D is positive, this must be true. Why did I even write minus 4D? Why would I do that? I'm doing that because I'm curious when this is going to be the case. So I want to kind of create a t squared minus 4D and create something that has to do with t squared. You might just say, why don't you just square both sides? Squaring both sides of an inequality can lead to very interesting things. And it's not always true. Okay. For example, I don't know if I want to make up an example off the top of my head. I will say, figure out under which circumstances can you actually square both sides of an equation. It's not always. Or for an inequality, it is always true for an equation, but for an inequality, it's not always true. Anyway, then if this is the case, then fortunately for us, it will always be the case as long as t is positive that we can square root both sides. It's an interesting thought exercise to evaluate why this is true. But we can square root both sides and preserve the inequality because t is positive. If t were negative, then this would be nonsense. And this is wonderful to know. If d is positive, we have exactly what we want. We know the relative size of these two quantities. Specifically, the square root is smaller than this. So the second eigenvalue must be the same sign as the first, because we're not subtracting anything big. This is positive. This is always guaranteed to be positive, but we know we're not subtracting anything huge for the second one. Whew. Okay. So lambda 2 is positive as well. And what do we have? We have a source. We have a new thing for our graph. If the trace is positive and the determinant's positive, we have a source. And again, as long as we're in the real part of the trace-determinant plane, we have to be under this repeated real parabola. But if we're in the first quadrant, t is positive, d is positive. If we're in the first quadrant, we have a source. So let's write that down. This section, it's going to give us a source. And sources can look a lot of different ways, but the idea is we can approach from here. We'll approach different speeds along different eigenvectors. Maybe the axes are our eigenvectors here, but we have a source. It'll look like this. What do you think is going to go over here? We'll find out mathematically. Okay, so that's what happens if d is positive. What happens if d is negative? Well, the exact same thing kind of goes, right? If d is negative, then when we subtract 4d from the left side, it makes it bigger. So similarly, the square root of t squared minus 4d is bigger than t, and again, t is still positive, which we still need. And because this part is bigger than this part, then the second root, the second eigenvalue, when we subtract, we'll switch the signs. If this is bigger, we have a smaller number subtracted by a bigger number. That'll give us a negative number. So our second eigenvalue would be negative here. We'd have a saddle. So if t is positive and d is negative, so if we're in the fourth quadrant, we have a saddle. All right, so if we're down here, we have a saddle. I don't want to make my graph look ugly, so I'm actually just going to tell you, if we're in the third quadrant, it's also a saddle. So everything in the third and fourth quadrant is going to be a saddle. We'll have that situation where it's like approaching along one and then veers away. Approaching along one, veers away. And again, maybe we have one of these eigenvectors behaves like a sink. One of these eigenvectors behaves like a source. And that's going to be everywhere down here. We can continue analyzing. The most of what we did, we've already mostly done the hard part. What if the determinant is 0? Well, if the determinant is 0, what do we get? The square root just becomes t. So one of our eigenvalues becomes t and the other eigenvalue becomes 0. Lambda 2 is equal to 0. So if the trace is positive and the determinant 0, we have that weird 0 case where we have like a whole, trying to remember what colors I use for this. We have like a whole line of equilibria. You remember this? We had a whole line of equilibria, and then one of them is positive, so we also have some sort of source behavior. That was just leaving this equilibrium line along the direction of the other eigenvector. You want to add this to it? You can. I always go the wrong way. But yeah, that's when the trace is positive, the determinant is 0. So you can add that here if you want. I'm not going to add it because it looks a little cluttery. You know what? I am going to add it. Why not? The book doesn't add it. But yeah, if the determinant is 0 and the trace is positive, we have that situation where again we have just like a whole, we have a whole like line of equilibria, and then it kind of behaves like a source outside of that. This one's not important. I mean, it's important. It's an edge case, but it's like a degenerate case. It's not very common. So maybe put parentheses around it. Maybe draw it nice and small. That's what we should have done. All right, so those are all the cases for if t is positive. If t is positive, the determinant has to either be positive, negative, or 0. We're going to do the exact same thing for suppose t is negative. And when you do that, you're going to get pretty much the same thing. If t is negative, we'll follow the exact same steps, the exact same logic. We're going to get more things. I highly recommend you pause the video. Say, okay, what happens if d is positive? What happens if d is negative? What happens if d is equal to 0? I recommend you pause. I still am going the wrong way. I recommend you pause the video and get those figured out. Short answer is it's going to be very symmetric as we might expect. This will be a source. Oh gosh, wait a minute. This is a source, right? I drew a sink. Yeah, D and T are positive. Should have been a source. This is a disaster. Don't worry, I planned for this. Da, 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 da. It's all according to plan. The source was when the sink was when trace was positive. The source was when the trace is negative. It's going to look very, very similar. Right? Your arrows are just going to leave. It's honestly embarrassing how often I draw the wrong picture for that. But yeah, eigenvalues are positive. It's a source. It is leaving equilibrium. And similarly, we can do another like degenerate case over here, and then the saddle will be true for all of that. And you might be noticing we're missing something from our cases. Positive t, negative t. What happens if t is 0? Well, if t is 0 and the determinant is positive, we have the center. If t is 0 and the determinant is negative, have we covered that? If the determinant's negative and t is 0, we just have plus or minus. We just have plus or minus this over 2. So it's still a saddle. They just have the same eigenvalue. So it's just a very nice looking saddle. So again, if d is positive, that was our center that we already looked at. If d is negative, it's still a saddle. It's just a very nice looking saddle. And if t and d are both 0, well, then you have a very boring matrix. If t and d are both 0, then everything's in equilibrium. You can plot that if you want. This is the phase portrait. Sorry, not the phase portrait. This is our trace determinant plane showing all of, again, there are more, but a bunch of, oh, wait, we are missing a very important situation, right? We're complex if we're above the repeated root parabola. We're real if we're below the repeated root parabola. What about if we're on the repeated root parabola? Here, we'll use a different color for that. If we're on the repeated root parabola, we're going to get one of two things. Well, maybe, right? That's, again, the repeated root is when we just have one eigenvector. And we have one straight line solution. Maybe it looks like this. And then we like kind of like curve. It's like kind of a spiral, but not really a spiral. It like tries to be a spiral. And if we're over here, it's kind of like a source. And if we're over here, it's kind of like a sink. And again, we're like approaching along one straight line solution. And here we'll be getting sucked towards it. Kind of behaves like it's trying to spiral, but it doesn't quite spiral. And again, we have a bit of a silly case at the origin that we're not going to plot. So cool. This looks made up, doesn't it? But the idea is, this is really, really powerful for a lot of different ways. The idea is that we can really see these boundary cases. If we're over here, we have a spiral source. Over here, a spiral sink. How do we go from a spiral source to a spiral sink? We get there with the boundary case of a center. If we have a spiral sink and a real sink, what's the boundary case look like here? It's like this degenerate case of kind of like a half spiral. If we have a real source or a saddle point, how do we get from here to here? That'll be when the determinant 0, and one of our eigenvectors slowly becomes less and less like positive. Sorry, one of our eigenvalues becomes less and less positive until it's eventually 0, in which case we stop moving along that second line altogether. And actually, if I want to be really consistent for this picture, let's keep the eigenvalue the same, actually. Right, then really what we have here is one of our, our whole y-axis is one of our eigenvectors in this case. So this is really what we'd have. And you can see that, right, it's positive in one direction, but then the vertical eigenvector becomes 0 and then becomes negative over here. And that's how we transition from a source to a saddle. Okay, so there's 3 different ways that we can transition. We'll call those, well, we have a name for those, but we're going to call them, I don't want to spoil it. I don't want to spoil it, but it's in a future video. I know this video was long. There's a lot of really cool analysis that you don't have to be able to replicate, but it is very, very cool and exciting, kind of putting together everything we've learned in this chapter. This is what we're going to use. And not all the time. Like, this is not something you have to memorize. This is something that is a cool way of seeing math and lets us do cool analysis. So We'll use that in the rest of this chapter, but don't get overwhelmed. This is fun math. Bye-bye.